All right, then welcome everyone to the first ASAM OpenDRIVE webinar. This is the first webinar after the release of ASAM OpenDRIVE 1.6, and this is only today a first jump into OpenDRIVE, and that will probably be followed by a few other webinars diving deeper into OpenDRIVE. There's already the first question that I want to mention before. Yes, we will record this session and make it available for everyone after the meeting. So don't worry about that. And we will also make the slides available after the webinar. Okay. Then what do we have planned today? So all those times I showing here on the agenda are in the Central European time. So we will start with the first part of the webinar. I will take or will answer all the questions that are gathered in the Q&A session or in the Q&A part of Zoom after around 40 minutes. Then we will have a short coffee break, so I can, oh, there's a mistake, that should be 3 o'clock. We will have a 10-minute coffee break so I can catch my breath after talking for about an hour. And then we will continue until 3:30, and I will take all the remaining questions after that at around 3:30. All right, so please use the Q&A tool in Zoom, and I will then answer all the questions that are in the Q&A session in the individual slots. Okay, so first of all, for today, I want to talk a bit about the current OpenX portfolio at ASAM. Just a few minutes. That is the current portfolio of the OpenX standards that are currently under development or has been released. So the first standard here, we have the Open Scenario that was released in March, as well as 1.0. That is about the dynamic scene description and scenario description. There are currently 2 further development projects running about Open Scenario. Then, of course, we have OpenDRIVE, where you will learn about more today. Then OpenCRG, I will touch OpenCRG today, what it's about, and just short, it's a detailed road surface description format that comes with a C API and the MATLAB API. Then we have the Open Simulation interface that works as a sensor interface for simulations. And then we've got OpenLabel, which is currently under development and will probably be released as a 1.0 end of next year or beginning of 2022. OpenODD is a recently started concept project where we are looking into how should an ODD represented as a file format. And apparently there is a problem with people can't hearing me. Okay. Could anyone just put into the chat real quick if they see the next slide, the OpenX portfolio? Because someone has a problem there. Okay, perfect. Yeah, and then what I just said, the OpenODD format, that is what it's all about, making an ODD machine readable, comparable, so it can be used in a simulation framework. And then we have the OpenX ontology, which is there to create an overall domain model over the whole OpenX portfolio. And we also created a example workflow how this all of those standards could look like in a scenario-based testing workflow. So we have we start here in the specifying part. We've got a study group that is about testing test descriptions. They're looking into that. Then we've got the OpenODD part. For scenario descriptions, we have OpenODD, then Open Scenario. For the static content, we can use OpenDRIVE and OpenCRG, and scenario pass-fail criteria are currently being developed in the version 2.0 of Open Scenario. Then for the simulation, so when you run your simulation, you might want to use materials. So there's a recently published standard by BMW that is called Open Material. In between these models and your simulated environment and your device under test, you can use ASAM OSI. And of course, for all the data that comes out of your simulation that might need to be labeled, is you can use OpenLabel that will provide methods and definitions and an annotation format on how you can label object data to make it, on the one hand, exchangeable, and on the other hand, of course, interpretable for everyone. Yes, and then of course in post-processing, you can use OpenLabel again, store your data, and once you want to retrieve your data again, there we are currently also working on scenario labeling and categorizing, so that OpenLabel can help you there as well. And as I said before, the OpenX ontology project is there to create that overall core domain model, so all those standards speak the same language. Now to briefly jump into the OpenCRG relationship, as all of those standards are already mature and OpenCRG is going to be released in November in the ASAM version. That's their relationship. So once you have an OpenDRIVE network, you can add several OpenCRG files to it, defining more detailed road surface descriptions. And of course, with using OpenScenario, you can drive on that defined road network. And with that, we can get started with OpenDRIVE. And as I said in the invite, we are going to, what is OpenDRIVE for? What's the strength and the weaknesses? So OpenDRIVE is a format on describing static road networks and can be referenced by OpenScenario. You don't need to, but we recommend doing that. And it will help you describe all the semantics of the road network, such as traffic lights, for example, or signals, road marks, how many lanes there are, what's the shape of the road, all of that. And that's the strength of OpenDRIVE, right? So having that precise semantic description of a road network with geometry, lanes, road marks, the traffic infrastructure. OpenDRIVE is designed to be interpreted by simulations and provides an exchangeable format. On the other hand, describing the environmental model and all the parts besides the road, that's not one of the strengths of OpenDRIVE. So there, in the concept project of OpenDRIVE, for example, we looked into how could we enhance OpenDRIVE there, either combining it with other standards or making OpenDRIVE more capable. Then OpenDRIVE doesn't contain any visual information, so it gives you the semantics, but once you want to visualize it in your simulation, that is something where the simulation itself needs to enhance the model. And junction modeling is very complex. What and why I can will show you a bit later. And if we have time in the end, we might even jump into the junction modeling itself. If we don't get there today, that will be part of one of the next webinars. All right, so when we look at OpenDRIVE and how this is set up, OpenDRIVE is centered all around its reference line. The reference line is the most important concept in OpenDRIVE because that spans up a coordinate system where the axis is called S and T, and attached to the reference line, you add the lanes that of course make up your road, and then you add all the features to that, and those are relative to the reference line. They can be placed, of course, in a global coordinate system as well, but when you want to move around your road, it is more handy to have all the signals that are besides the road attached to your reference line, because once you move the reference line, you also move in relation to that all your objects beside the road. In the transfer project of OpenDRIVE, we created an UML model, and a part of that is, you can see here, that where we came up with the core class that contains everything you need to know about OpenDRIVE. You can download the full UML model from the ASAM webpage and dive deeper into that and see how it's set up and how all the relations are. So for today, we are not going to jump into the UML model that deep. We are going to stay focused on examples and concept that make up OpenDRIVE. Yes. So if we have a look coming from the UML model to the XML structure, this is pretty much all the headers you can find in OpenDRIVE. So it's all enclosed by that OpenDRIVE bracket up here, followed by the header. The header pretty much contains meta information about the file, who made it, what's the name, what's the ID, when was it used, what OpenDRIVE version is used, whatsoever. Then you define all your roads and everything that is necessary to define a road, followed by the junctions. Here you can reference external controllers. As controllers are dynamic parts, they are not defined within OpenDRIVE. So controller would usually be connected to a traffic light. And then down there you have the junction group that is usually made up to, or with the junction group, you can put several junctions together, for example, for roundabout. So if you think about a roundabout, that is a circular order of several T-junctions. Yes, and that is pretty much the whole OpenDRIVE. So we are going to have a look at OpenDRIVE and the several parts. And we are going to start with geometry and all the basic parts of OpenDRIVE, so you can get an understanding what there is to OpenDRIVE and how you can use it. And that is why we start with the 3 different coordinate systems that are defined in OpenDRIVE. So we have the inertial coordinate system. So in the inertial coordinate system, your whole road network lives. So for example, you want to create a larger road network, and you would place that whole road network in your X and Y coordinate system. That coordinate system can be georeferenced, but you don't need to. If you do so, we recommend using an inertial coordinate system and having that georeferenced instead of using global UTM coordinates to minimize the floating point error calculations from the calculations. Then we have the reference line system, as I said before. That is a Frenet coordinate system that runs along the road. And then we have a local coordinate system that is usually used to place object or define objects in, and then place that local coordinate system wherever that object is going to be. They are going to follow examples. So of course, all of those coordinate systems can be turned, pitched, or rolled. And here there's a description on how that looks like. So once you, for example, change the heading of the coordinate system, that's a rotation around the z-axis, as you can see there here. If you have pitch, then you turn around the y-axis, and if you have roll, you turn around the x-axis. And how that looks if we have a cube. So now we look right on top of the cube, heading, pitch, and roll is all 0. Now we start and increasing heading, so now we can see the side as well. When we increase pitch, we can now see actually 3 sides. And now when we apply roll, then we see how the whole cube tilts. And when we come to the reference line coordinate system, there we can apply heading and roll similarly. What we don't have here is pitch. And that is important to remember, that there is no pitch for the reference line system. And why this is important and why we need to remember that, I will talk about later when we come to elevation of the reference line. So here again, heading is all around the z-axis or the h-axis in that case, and roll is around the s-axis. Yes, and important, no pitch. Yeah, so the reference line system, there you have your heading, and the heading is caused by the geometry of your road. So when your road makes a turn, that changes, or that is represented by the heading of the reference line. And so the heading in that case is caused by the geometry. Then roll is caused by super elevation. So if your road is tilted to a side, so now we are looking here directly onto the s-axis, and your road is tilted, for example, in a steep turn or on a highway to let water run down the side. That's when you apply super elevation, and that is roll. And what you can see here is that the whole coordinate system is tilted around the s-axis. And here the whole coordinate system is turned around the h-axis. And now we come to the part where we don't have pitch. So once your reference line gets elevated, your coordinate system stays in level ground on here part 0 of the global inertial coordinate system. So what's the implications of that? So when you increase the elevation of the reference line from a bird's eye view, the road just stays the same. So if it's 100 meters long and you have an elevation of 20 meters, it just stays from a bird's eye view 100 meters long. But in reality, when you have to drive up, then of course the way you have to pass to get to the end of the road will be longer than that. So please keep that in mind when you model OpenDRIVE roads, that elevation increases the length of your drivable road, not in the plan view or when you define the reference line. So yes. And this is a road now placed into a inertial coordinate system. So what you can see here is the s-axis that goes along the road. And you can see that the s-axis is always, in that case, in the center of the road. It doesn't have to be in the center of the road. And we've got the t-axis always perpendicular to s. And that is important to remember and to know. And of course, what you can do is calculate or transform coordinates from s and t into the x and y coordinate system. So that is always possible. But if you have a look around here, especially in that case, if you go into a large t coordinate and here, they will probably define the same coordinate at some point as they would touch each other. So that is always something to see and keep in mind. Yes. All right. So when we continue and think about the local coordinate system, what I said before is that the local coordinate system is all about the objects and that the objects live in that local coordinate system. Then we have a u, v, and z coordinate system here, and that has the heading and also u and v, and heading turns around the z-axis, same with the inertial coordinate system. We have pitch for the local coordinate system that goes around the v-axis, and then we have roll that goes around the u-axis. So pretty similar to the inertial, just that u and v and x and y are different names. And of course, applying that to our already known cube, that will look like this. Okay, so the question is, why would I need a local coordinate system? Why can't I just place all my objects in my inertial coordinate system? Well, let me show you this. So for example, you want to place a curve for whatever reason in your with the mathematical functions in the inertial coordinate system, and at that point I would have a problem because I would have 2 points on one curve, and well, math doesn't like that really much. So what I can do here, I can use a cubic polynomial for that, place my cubic polynomial in a local coordinate system, and then, well, that works, right? So there's just 1 point for each u coordinate. There's just 1 point here on the v-axis, and if I place that local coordinate system in my inertial coordinate system, then I'm good, and then I can transform the points from the UV coordinate system into the inertial coordinate system. And that's where heading comes into play. Yeah. And these are the formulas. So that's simple mathematics. Yeah. All right. right. So what I said before, that you should, when you want to georeference your road network, you shouldn't use the global coordinates or UTM coordinates for that. That's what you can see here. So pretty much the recommendation is to define your road network in your small inertial coordinate system and then apply a georeference to it. Because if you have a look around here, you can see already quite big numbers. So you will have less digits behind the comma for your calculations. And if you use small numbers, that will decrease the floating point error. And in large road networks, that can cause minor problems, minor gaps. Yes. So that was the basic excursion around geometry and the coordinate systems. Now we will get into what geometry elements can I actually use to define my reference line. So here we have the UML model again. And here on the side, you can see the geometry elements, or we will go into more detail on each of those. And there are a few of them. What we did in OpenDRIVE 1.6 is that we deprecated the poly 3. I will talk about the poly 3 geometry, but we deprecated it because it is rarely used and the param poly 3 is way more capable. Okay, so the 5 elements you saw in the UML model are displayed here again with small images of them. So a straight line, quite obvious, a straight line. A spiral, you can see here, that is a curve with a constant change of curvature. So for example, from a straight line into a tight turn, then an arc has a constant curvature, and of course, a cubic polynomial or the parametric cubic polynomial. They're just a function, third order. So why is this important with the curvature? So of course, if you drive on a straight line, you don't need to turn your steering wheel. So you just sit there, go straight, and there will be no change of the steering angle over time. The spiral is a function of the steering angle over time. So pretty much you start turning your steering wheel into one or the other direction, and you will have a smooth transition through the turn. Once you are in the arc doesn't have a change of curvature, but your steering angle at that point would stay constant. So that would give you, that constant turning radius. And then we have the cubic polynomial, the parametric cubic polynomial. Of course, here your steering angle would follow the curvature of the reference line. So what are the basic parameters and attributes of each and every reference line element? So each and every reference line element has an S coordinate. So where does it start on the reference line? That is in meters. And then X and Y coordinates. So you can place them in your inertial coordinate system. So that's the starting point. Here we have the heading, and that is defined in radians, and then the length of that element. So all the units are here as well, and that's what you can find in the specification as well. And S can't be negative. So S pretty much goes along the S-axis and can't be negative. Same with the length. All right. So if we now look on defining a basic straight line in OpenDRIVE, it's pretty straightforward. We have the X and Y coordinates here, and we've got an S position of 0, so our reference line starts right here. We've got a length of, in that case, 57 meters, 0.28, and that pretty much is the one we have here. And the line attribute is empty because we don't need more than what we have here to define a straight line. But still, you need to add that line attribute so your interpreter knows that you're talking about a straight line here. If we go in for the arc, we have a similar definition. So what I said before, each and every geometry element has the x, y, heading, and length. And now we have the arc here and describing a constant curvature for that arc. So in that case, this arc would be represented by those numbers. And I put in here how you could calculate your u and v local coordinates if you would put that into a local coordinate system. Yes. The spiral, there we have a constant change of curvature. And that is what you, of course, define in your XML again. So you would start as here at 100, for example. Then you have your inertial coordinates again, the heading, how's the heading of the spiral, and then the length. And then you start with the curvature at the beginning of the spiral and what shall be the curvature at the end of the spiral. So that pretty much gives you that smooth transition from a straight line into a curve. The cubic polynomial is a polynomial third order. So that is a u and v at that point. And yes, so the here again we have the already familiar s, x, y heading and length, and then the poly 3 will come with the parameters in the XML description, and that polynomial we will encounter quite often throughout the OpenDRIVE specification. That is used quite often, and yeah, that's how a poly 3 could look like. And then we have the last but not least, the parametric cubic polynomial. There you have two equations of third order that are u and v local. And here you have the equations for that are, I'm just seeing I'm missing a u here. That needs to be here. So yeah, but it's the c for the u equation. And what I made up here is a very simple and not that accurate, but well, simple Python programming example, how you could calculate a parent poly 3 and getting the points, the u and v points. So pretty much defining all the parameters and defining also the sample points, right? That would be p. And how many points do you want to calculate on your parametric cubic polynomial? And then return all of those. You need to make sure that in your implementation, you always get the last point as well. So your increment don't skips that last point of that parametric cubic polynomial. All right, so here we have the definition of a parametric cubic polynomial element that is actually taken from a real world measurement. And the link is up here where you can find that real world measurement where I've got that third order parametric cubic polynomial from. And here you can see also the A, B, C, D parameters of the U equation and the V equation. And then you've got also the P range. So that will be the sample points. And of course, the already familiar parameters for geometry. And of course, you can have two of those, two different. And if you see up here, here we start at 0, s equals 0, and the length is at that point 65.65 meters. And the next part, the next geometry element starts at exactly that s coordinate where the other stopped. So they join right together. This one has a length of 111 meters, and the wall structure is the same. So we've got the first one, that is defined from 0 to 65. And then we've got the second one that is defined from 65 to, well, if we calculate that together, something around 170, 76 or so. And of course, that's how you would join them together. And that is pretty much what you do with all the geometry elements around the road reference line. And the parametric cubic polynomial is very good if you want to create the road reference line from measurement data. But OpenDRIVE is often also used to create synthetic roads for simulations. So you create your road network with all the problematic parts of the road network you want to have in your simulation. And there you can use the other three geometry elements, such as line, arc, spiral. Yes. So you would start, for example, if you want to create an easy turn that is a straight line, where of course you have a constant curvature in that case of 0, because you're just going on with that straight line. Now, if you want to start turning into a curve, you would add a spiral to it, where you would have a change in curvature. So you would actually drive into that curve, turning your steering wheel, and add an arc. And there you would have that constant steering angle that is that comes with driving through a not changing curvature. And now if your curve opens a bit, then you would add another spiral to it, and your curvature would change again. And then you would add another arc, for example, or a straight line, depends. But probably from that point down here, you would add either another spiral to get to 0 if you want to have a straight line, or add another curvature part, arc to it, so you can continue with a constant curvature. And this is very important, keeping that steering angle in mind when building roads, because if you want to have a smooth traffic flow of your simulated traffic that can follow the reference line, is not jumping around, because a physical car can't jump the steering angle from, for example, 0 to a certain value. It needs to go there. That will help, having those roads built using that methodology. Yes, and with that, we covered all the geometry elements and the coordinate systems. And now I'm going to jump into the questions and see on what questions I can answer already. So the equations for the spiral will be, you can find them later on in the published slides. Then a heading, pitch, and roll are in radians. Yes, that is correct. Then, okay. Then we have the question, to date, the center line can be described as a clothoid. This is very convenient for particular geometries. However, the edges, border, width must be described through polynomials. This can lead to cases of singularity in the SN reference system of the center line. For example, if you have very high curvature, you want to introduce the possibility of describing border like spiral. So yes, you could describe the clothoid. That would be possible. So if we go back to the arc, there we have the arc again. You could do that. I wouldn't recommend doing it only with clothoids. I would actually recommend doing what I showed before and trying to get that smooth curvature and don't try to have jumps within the curvature, or if you have problems with your calculations, ending up with gaps in the reference line. That could happen as well. Then, are there any production libraries available for converting between the road and the inertial coordinate systems? I guess what you could do is use NumPy or anything like that to convert between coordinate systems, but I'm not aware that there is anything open source available for especially the OpenDRIVE case. Of course, all the simulations that support OpenDRIVE will be able to do that, but I'm not aware of any open source library. Then we have the question, is poly3 convenient because road layouts are actually sometimes defined in that way? Otherwise, it might be easier to process a series of arcs and spirals. So that depends on your use case. If you want to create a road network using a measurement data, then I would recommend that you use the parametric like in this example here, because it's a bit easier for your machine to optimize 8 parameters to match your reference line to the real world. But if you have synthetic data, or you want to create a synthetic road network, then it would be a bit easier for the user or the builder who is going to create that road network to piece together straight lines, arcs, and spirals. Then let me see. Yes, the spiral formula I can provide, and that is also in the, there's also reference implementation that you can download from the ASAM page. Then let me see where there are more questions. So is the inertial coordinate system similar to the vehicle navigation coordinate system fixed to the rear axle of the vehicle? No. Well, it's both a Cartesian coordinate system, so in that way, yes, they are similar. But the inertial coordinate system in OpenDRIVE is static and stays where it is, and you pretty much just put your road network into that coordinate system. So if we have a look over here, and your vehicle coordinate system would actually move around within that inertial coordinate system. Let me see if there are any further questions. Will there be a database with typical, where did the question go? OpenDRIVE examples? I think there are companies selling those OpenDRIVE road networks. There's also an initiative from the Automotive Simulation Center Stuttgart that are trying to create a marketplace where you can, for one, publish OpenDRIVE files and also get OpenDRIVE files. That's the invited marketplace. But I'm not aware that there's a publicly available database for all sorts of OpenDRIVE files yet. There's sometimes always examples, and the OpenDRIVE standard comes with examples as well. And I also linked a small page from German government agency here, where you can download 2 parts of the German Highway A9 as an OpenDRIVE file. Okay. So then there's the question on how the GPS reference is attached to the OpenDRIVE. In the header of the OpenDRIVE file. Now if we jump into the Georeference. So in the header of the OpenDRIVE file, you would actually put in those Georeference coordinates, so you know what reference to apply to your inertial coordinate system for your transformation. So that is directly in the header of the OpenDRIVE file. Okay. Then let's see if there are more questions. Will the length information of potential duplication, could it be derived from other information associated with geometry? Yes, it would be possible to derive. So if we go to another example. So for example, what you could of course do, if you have the inertial coordinates of the starting point of that line, and you have the inertial starting point of that spiral piece. Of course, you could calculate the length of that straight line. And the information that is provided with the length of that part is, of course, in some way redundant. But it will also help you check if you made an error in your calculation. And then it could also help you avoid either gaps. Sometimes it can cause gaps as well if the length is too short or the coordinates here don't match. But yes, you can derive the length from individual geometry elements from the starting point of the next one. But for example, if you don't have a next one, you would need to either provide an endpoint where there is no field in OpenDRIVE yet. And so we have the length. Then there was the question if this session is going to be recorded. Yes, it will be recorded and provided later. Okay, more question. Okay. Then there is the question for any editor for editing OpenDRIVE files. There's also already an open GitHub link to that. I'm not aware of that OpenDRIVE editor. So check it out. Try that. You could use any text editor as it is just plain XML code. And ASAM doesn't provide a tool to interpret or edit OpenDRIVE. Okay, then there is the question between, I don't understand the difference between S and length. So the S-axis goes, along with the road, and length pretty much describes parts on that S-axis. So for example, if you would have, let's say that road element is 100 meters long, and we go and start S equals 20, that would be probably somewhere around here, and S equals 80, that would be probably somewhere around here. That length would describe the part in between of those two coordinates. So that would be length 60, and the S coordinates would define the start and the end of that length. Hope that answered that question. Let's see if there are more questions. Do you recommend any viewers for XODR? Unfortunately, I can't recommend any viewers on OpenDRIVE, as there are many simulation tools out there and I don't want to favor any of them. So no, I can't recommend one. Yes, the link to the A9 German highway will be in the slides and will be shared. And then any plans on OpenNDS and OpenDRIVE converter. So as far as I'm informed, NDS is not an open standard as OpenDRIVE is. I think there are projects by a few tool vendors to create such a converter, but I'm not aware that any is going to be published as open source tooling. If anyone knows more about that, please share that in the chat. Okay. Is it possible to convert an OSM file to OpenDRIVE with correct georeference? In theory, yes, it is possible to do so. The problem with the OpenStreetMaps is that it comes with different kinds of quality of information. So sometimes you've got really high and a lot of information on your road network, where you could probably have a rather good OpenDRIVE file from that. But on the other hand, sometimes you barely have that, straight line of the road in extreme cases. So the information provided in OpenStreetMaps can be used to convert to OpenDRIVE, but you would need to create a converter for that. I think there are some projects out there tackling that issue. And then we have a question in the group chat. Why are there so many redundant properties in the geometry definition? Length of the geometry is derived quantity, as is the integral over preceding geometries. Yes, that's true. And we talked in the OpenDRIVE concept project about all those redundant information and if we could leave them out of there. And the result of the discussion was, no, we don't want to leave them out of there, out of the definition of all the geometry elements, because they can help the user to better understand the file if you read the file, and it could help you avoid or avoid errors in your road network. So you are invited to join the next project. If you want to know more about how to join an ASAM project, either go directly on the ASAM page or you can contact me as well. Okay, so what other questions are there? With the length information of potential duplication with X and Y and length, could it be derived from other information? Okay, so we already got that. Okay, then there we already have the link to the Euler spiral. Perfect. Then we have. Okay, so then there's the question: any plan to come up with an OpenDRIVE editor? ASAM doesn't plan to come or provide an OpenDRIVE editor, as we are not a tool vendor and we don't want to be competitive to the tool vendors that are members of ASAM. What we are doing is that we are providing an open source platform where people can provide open source tooling and be responsible for that. So, but then it will be published in the ASAM ecosystem and members will be aware of that. But there is no plan to come up with an ASAM OpenDRIVE editor. Okay, further questions. Then we have a question, is it possible, it is possible road data can be created in automatically like road runner tool? I guess so. I'm not that familiar with the road runner tool, so I've seen a few demos, but never used it myself. I know that there are tools out there that are quite capable of creating those road networks and helping you adjust them automatically. I would recommend going to Vector Zero to ask them. Okay, we've answered that one. Then there's the question, what is the difference between poly3 and param-poly3? Let me go back to that slide. So the difference here is that you calculate your v coordinate directly from U. You've got 1/3 order polynomial and you only get those 4 parameters to define your road network, or the reference line element in that case. And if you go to the parametric cubic polynomial, that actually gives you 8 parameters additionally to the arc length of that element and lets you optimize a bit further. So if we have a look on the 2 polynomials here, they're actually calculated a bit. You've got just more ways to match and more optimization potential to match your reference line onto that real world data you have. And of course, that is a bit more complex here. But the use case here is not that you find all those parameter values yourself. That's an optimization problem. Okay, if there are no further questions, there's another question. To reduce errors in starting X and Y coordinates between roads and geometry, why not only use predecessor successor as a default if the roads are connected? Hence, the X and Y start would not be a problem. So there is the successor and predecessor concept that is introduced with roads, what I'm going to dive into after the break. And we talked that through as well. And that will produce a few other problems. But I can dive into that after the break. Any further questions? Okay, if there are no further questions, we have a 10-minute break. We will do so, but we can't create them on our own. All right, then we will continue. And now we will jump into roads. So a road in the concept of OpenDRIVE has several elements. It's the road itself. It has a length, has is it part of a junction or not, has an ID, you can give a road a name, and you can give the road a rule, and in that case, that is it right or left-hand traffic. Then we've got the road type, the country code, then, for example, a speed limit or a max speed in that case. Then we have other different elements, for example, links, lanes, is it a railroad or not? Because in OpenDRIVE, you can also define rails that are defined very, very similar to roads. So we have road signals here. And then, of course, we have the road surface, the lateral profile, elevation profile, and the plan view. And we will now go into those down here. Those we've seen the lateral profile, we've seen that there is. And we will go into those and into the road link. Lanes, objects, and signals, and all the other elements. I'm not going to touch in this webinar. This will be for part 2. So if we define a road, we will take that very, very simple example of a straight road that is defined between two other roads. It has a broken line in the middle. It's 100 meters long, and we have the linked predecessor and successor road. In that case, we have the predecessor road ID 2, or road 2 in that case, and the successor road 3. So what do we need to do to define a road? So first of all, we need to define the road header. And there we have the mentioned rule. So in that case, we have right-hand traffic. The name of our awesome road is going to be example road. It has the length of 100 meters. It's the ID 1, and we are not part of a junction. Then, of course, we need to define that road link. So we define predecessor and successor. And here we have that logic combination. Where do I come from? Where can I go? So we have here the road ID 2 that was in the beginning, and then we have road 3 that follows our road 1. And then, of course, we have to define the geometry as a reference line that the road can follow. And in that case, of course, we will use a straight line. In that case, that is going to be 100 meters long. Doesn't have any heading, starts in the inertial coordinate system at 0, 0, and of course at the s coordinate 0. And then we define that as a line element. The fourth part is, of course, now I have my basic logic road box, and I have a reference line to it. But what I don't have yet is lanes. So now I need to define the lanes. And for that, I'm going to define the lanes. I'm not going to dive too deep into lanes because that is going to be part of the next webinar as well, because that would be too long for today. But I will want to show you that how lanes are defined. So we've got the lane ID, and the ID of a lane increases or decreases with the direction of t. So if you're on the positive side of the s-axis, so t is positive in your coordinate system, your IDs are positive. And if your tx, if you go to the negative side of s and t is negative, then your ID is going to be negative as well. So for example, the first lane, so you always have the center lane that is pretty much has the width of 0 under the reference line. And then you have the left and the right lane, and those will be always 1 and -1. Then the next one will be 2 and -2, and so on and so forth. And of course, each of the lanes has a predecessor in the predecessing road. So this predecessor here would be the lane ID 1 in road 2, and the successor here is of course the lane ID 1 in the succeeding road 3. Then we have the border, so we need of course to define the width of that lane. And here we have the third order polynomial again. So we've got the A, B, C, and D. You could define an S offset. Then we have the parameter A, and that pretty much gives us, as the rest is 0, a straight or the constant width of the lane. And in that case, it's 3.57 meters wide. Then we have the road mark of, in this case here. And there we have the road mark. In that case, the broken line starts at S0. It is broken. It's a broken line. So it's the standard weight, so it's not like a bold line or so. The color is standard, so you could choose from a small variety of colors. And the reason the color is in here, it's because sometimes different colors enforce different rules or enforce different validity. So for example, in Germany, if you have yellow road marks in the construction site, those overrule the white road marks. So this color here can be related to the traffic rule. Of the road mark, in that case, it's 12 centimeters wide. And is there an implication on that road mark regarding the lane change regulator? So is there any regulatory things I need to consider with that line? And in that case, there's none. So if we would have a solid line, then there could be no passing, for example. And of course, here I have the height of the road mark. So how high is it? And in that case, it's about 20 millimeters, so 2 centimeters, so that's pretty high. Yes, and then here is the type of the road mark again, just to give you a glimpse on how that looks like when you define the lanes. And that is the example on defining a road in OpenDRIVE, where you have a straight road that will give you right-hand traffic, in that case the example road with the length, defining your links, where does your road link to, then come up with the plan view. So in the plan view, you define all the geometry elements. And of course, if we would have a curved road, as we had in the example before, we would have many more geometry entries here containing, for example, parametric cubic polynomials or spirals, arcs, and lines and stuff like that. Yeah, and then we have the lateral profile, where you define a profile perpendicular to S. For example, if your road is maybe tilted a bit, or if there's a shape you want to have to apply to your road, then you can use the lateral profile. Then down here you have lanes, and then you can apply objects, signals, and surface as well. So that's where OpenCRG comes into play. And all of this pretty much makes up the road definition. Now we have our road here, and we saw before that that road is not part of a junction. But what if my predecessor road is part of a junction? Then in that case, here I have a junction. Now some may say, okay, maybe I should cut here, and this would be a normal road, and then the junction would start here. But for that example, it doesn't matter. So we have a connecting road here in that junction with the ID 2, and the predecessor of road ID 1 is in that case not road ID 2, but rather junction with the ID 2. Because what happens in junctions, I briefly want to talk about that. In junctions, the connecting roads are overlapping, which shouldn't be the case for normal roads. But in the case of junctions, this is allowed. And of course, then from that point, I have two roads connecting to the previous other roads. And if I would choose one of the roads as a predecessor to that road, that's not the best way, because then maybe the other road doesn't have a successor. And so we just take the whole junction as a predecessor. Yes, and then of course I have my road ID 3 back here. All right. Yes. Now we defined the linkage of the linkage of the roads. And now we defined the roads. Now we can link roads together. And of course, there are a few ways how you shouldn't do that, and there is one preferred way to how to do it. So of course, doing something like this can cause problems because you've got a gap in your reference line. And therefore, of course, you will have a gap in your road surface. And that might be even very, very tiny, but can cause problems, for example, when you use your that OpenDRIVE file in, for example, physical driving simulators. That would fall into those gaps, because there is no such thing as a ground besides the road in OpenDRIVE. Then we can have overlapping lanes, lines here, and that would cause an overlap. And depending on how your elevation is defined, or how the lateral profile, the shape of the road is defined, that can cause troubles as well, or steep gaps, breaks. Then what sometimes happens and is basically allowed in OpenDRIVE, but not recommended, but really not recommended, is that you align two straight reference line parts, or that you align two reference line elements that don't have the same heading at these end or starting point. And in this case, this is pretty clear. We have a overlap here, and we've got the gap up here. Yes, so that can cause trouble depending on the fidelity you need of the road network in your simulation. And of course, what you don't have here is as well is a smooth transition for your steering angle. And now, of course, this is the preferred way. The heading here at the end point and the starting point of each of those elements is the same. And with that, you will get a smooth transition from one road into the next one. So how can I align roads as well? So of course I can do that. That's quite obvious. Have two road elements, link the same lane IDs together. That is pretty straightforward. I can define the same road with the same driving direction like this. So the direction of the reference line is independent from the driving direction. So this lane here, I could still drive all the way up here. So that is allowed as well. Then, of course, if I'm allowed to do this, I'm also allowed to do this. And what you see here is how the lane IDs change depending on the direction of the reference line. Still, this doesn't have any impact on if this is which way you are allowed to drive that lane. So if this is right-hand traffic, you would drive down here this way and the upper lane in this direction. And this is something we decided not to allow because it will probably cause trouble for many simulators that you have a jump in the reference line if you're not in a junction. There are cases where this is a necessary construct within a junction, there it is okay. But if you're outside a junction, this is something we said in the standardization project, this is not going to be allowed. And here is the example I just mentioned. So for example, if you are in a junction and this is so the box here defines a junction. So for example, you're on a highway and the highway is splitting up. This one is going maybe to the north and here you're going to the east. And then you would define your connecting roads in your junction like this, because obviously there's no other way on how to define this road down here. Yes. And with that, we covered the definition of roads. Yes. So now we are going to go towards the elevation, super elevation and all of that. And so defining the actual shape geometry of the roads and adding more features to our road and creating lateral profiles. So what are the things I can actually add to my road? I can have that elevation profile, what we saw before, when I talked about the missing pitch of the reference line system. Then we've got the lateral profile that is perpendicular. Then we have, of course, the lanes, what we saw before. We can have signals. We can place objects on the road or beside the road. And we have the link information and user data is where you can put in additional data you need maybe for your simulation. But that's pretty much a free field for you. Now here are the 3 shaping mechanisms in OpenDRIVE. So the first one is road elevation, and we saw that image before. So here your reference line goes up or down, and this defines the shape of your road along your S-axis. Now if we look to super elevation, that is where your coordinate system is tilted, and that is pretty much perpendicular to S and along the T-axis. And then we have the road shape. This is pretty much using the third order polynomials again, and that is also perpendicular to the S-axis. And you can have the reference line at any of those points here, but in this case, of course, the S-axis would be at t equals 0. So if we now go to the elevation part, here we have the formula for the elevation, and that defines all the parameters again, and we have the already familiar third order polynomial that describes this elevation profile here. We've got S, we've got T, depending on the starting position, and then we've got A, B, C, and D. Now, super elevation is defined in the same way. So we've got the same parameters, but there's a slightly different but important difference. In the elevation profile, A is defined in meters, and here it is defined in radians. So A is an angle, and that is important to remember when you calculate your values, because otherwise it would be you would end up with wrong results. And of course, that's a tilt around the s-axis. So in here, you turn the whole coordinate system and the whole road as well. And now there is, of course, we talked about the impact of the elevation on the road, that with increasing elevation, you will stretch the length of the road in driving, from the driving perspective, but not from the bird's view. And something similar happens when you apply super elevation. So if you have your level road with no applied super elevation, and for example, now you want to add this crazy angle of 22 degrees, which I wouldn't recommend for normal driving roads, then of course, how will that look like in the end? So we've got the first example here, and I will tell you which one is correct, where you tilt that road, and this is the plan view or the bird's eye view. And if we have the same mechanism as when applying elevation, then that would actually stretch the width of your road, and depending on the angle, quite dramatically. Then the second option we have is that in the plan view, your road gets tighter, and the actual drivable road stays the same. In this example, the coordinate system is tilted with it. Here, the coordinate system stays the same. And here, we've got the same thing, but with a rotated coordinate system. And actually, how it actually is supposed to be is option number 2. So once you add super elevation to your road in the plan view gets smaller. So for example, if you have an editor that only provides you a top view of the road and you apply super elevation, and then the width of the road doesn't match what you actually put into the XML file, that is probably okay, depending on the angle. So you should take the angle of the super elevation into account when you check the width of the road or the lanes. Yes, and then we have the lateral profile. And here again, our good old friend, the third order polynomial is again with our parameters A, B, C, and D. And those are the parameters of the third order polynomial. And here you can see how those are applied. Yes, I'm not going to read all of that out. It's quite obvious, and I have an example later on. So here you can see the formula, and then I've just found a mistake here. So that should be a multiplication sign. So it's A plus B times delta t plus C times delta t squared plus D times delta t to the third order. So I will correct that before providing the slides to everyone. Yes, and then we have our familiar attributes of the lateral profile. Then we have S and T, of course, where is it supposed to be applied to, and then the 4 parameters. So I could, for example, define a road shape like this, or you could probably define something like this as well. And of course, what you can do is add different lateral profile definitions next to each other if you want to have a more complex road shape, for example, when you want to define ruts or so. And how that could look like, I want to show here in that very simple example where we have 4 shape definitions at 1 S position. So if you look here, we always have that S equals 0, S equals 0 here. And if the first definition of the lateral profile here starts as T minus 4. So we start way over here. We look onto the S-axis, and that is 1 meter. So all of the constants here and all of the parameters are 0. So there is no applied lateral shape. It's all 0. And it's for 1 meter. And there's no change in height as well. If we go now to the next definition, there we have a slight increase in the height of of a road by 15 centimeters per meter. And that means going from t minus 3 to t minus 0. So I have here t minus 0. Here's b, which equals those 15 centimeters meter per meter, or 15 centimeters per meter. And then I will end up with a height at t equals 0 of 45 centimeters, respective from where I started from. So my next lateral definition here is from t equals 0 to t equals 4. And here I will lose 10 centimeters per meter. And I can also see that A starts at those 45 centimeters I previously inclined. And then the last, I have a straight element where I am 5 centimeters above ground going for the last meter. Those lateral shapes are not bound to lane or lane definitions. They of course can be. So for example, if you've got a bicycle lane that is tilted like this, and then a driving lane that is tilted like this, and this could be sidewalks, but there is no semantic linkage between lateral shapes and lanes. So this could also be a rather wide 7-meter lane if you want it to be. And if you want to use third-order polynomials to define those lateral shapes, you can do that using those parameters. Now we can define the lateral profile, and maybe we want to have a more detailed possibility or more sophisticated possibility to define the road surface. And that's when we can define or add OpenCRG patches onto the road. OpenCRG is a very detailed way of modeling road surfaces, and you can just stick them onto the OpenDRIVE road network. And that's it. So we have the attributes here again. You pretty much define the starting position and the ending position of the window where you want the interpreter to interpret the OpenCRG file. You can also define the orientation, the mode, and the mode is very important when attaching OpenCRG files, and I will talk about that a bit later. And also the purpose, what you want those OpenCRG file to do. Because OpenCRG pretty much just contains numbers. So you can either define, okay, please interpret those provided numbers as elevation, or interpret those as friction values. And then I can have an S offset as well if necessary. Just to really quick show you what OpenCRG is, it's a curved regular grid providing those elevation values. And that's an example from the upcoming documentation from OpenCRG that was done with the MATLAB API, often a cobblestone example. And you could patch that onto any OpenDRIVE road if you want to. Now, if we have a look at the CRG format, we have a UNV coordinate system. So that is very, very familiar because this is the same as the local coordinate system in OpenDRIVE. And here, so we can take that coordinate system and use it to place the CRG grid onto our road. And that is what we can do. So I talked about before regarding the attachment modes, and the attachment mode attached actually puts the OpenCRG patch somewhere on the road on specified coordinates. That can be either S and T directly, or you can apply an offset to it. And in the attached mode, the shape of the reference line within OpenCRG is ignored, and the CRG patch will follow the reference line shape of OpenDRIVE. Also, OpenCRG values will only be evaluated as relative elevation values. So it's always added on top the elevation that has already been defined in OpenDRIVE. Then I have the genuine mode, and in genuine, I can turn and put the OpenCRG file at any point on the road, how I like, and then the reference line shape of the OpenCRG file is taken into account and will not follow the reference line of OpenDRIVE. And then, of course, if we have a look at the mode attached, and we before had the parameter orientation, what I could also do is say, okay, if the orientation is same, this is a familiar picture, just a bit different than we saw before. And that is how you can calculate your U and V coordinates in SMT. But if I choose the value opposite for the orientation, this pretty much turns around your CRG grid. So if you have a look at A, B, C, and D on those letters on there, so they're just there to show what happens to the rotation, then you actually turn this whole CRG grid around that point here. And you also turn the whole coordinate system as well. And these are the formulas to then calculate the points. Yes. Okay. So if we have a look on the attached mode in the form of how is it applied to OpenDRIVE, then we can see here that is added on top on the elevation, and our window where we said, please interpret my CRG data could be larger, and here you would just fall off the elevated values from OpenCRG, but that probably wouldn't be too big of a drop, and you would continue to drive. And here, of course, we can have the start window. If we have the CRG attached 0 mode, then you would have a problem. So if you define attached 0, in the interpretation window of OpenDRIVE, the elevation of OpenDRIVE is completely ignored, and only the values from CRG data is taken into account. So if your CRG data doesn't cover the whole window from as start till as end, you would fall into a deep hole here. So that is important to take into consideration when adding CRG patches onto OpenDRIVE roads. And then we have the mode attached 0. So this is how we should do it. So that the CRG patch at least covers the whole window. Yeah. Okay. And that pretty much gives us all what we need to know about the road definitions. And actually that here is too much, so there's no lane section. We will talk about lanes the next time. And with that, we are a bit over time, but now we'll answer all the questions that are there. And I will start here. Are road markings applicable automatically to both sides, edges of the road lane? No, you need always to define the road marks, and the road mark, so usually road marks are objects, and you need to place them, for example, if you have a turning arrow as an object on the road, and lines are defined to the lane and the side of the lane where it should be, but they're not automatically applied to both sides. But for example, if you have lane ID 1 and lane ID -1, the middle line you would only define in one lane. Is there any example on exporting OpenDRIVE file to Kala? I think Kala has an OpenDRIVE support, but I don't have an example. Okay, I will take your recommendation into account. In slide 48, is the blue -1 stand for, and what is the yellow -1 stand for? Okay, let's jump back to slide 48. All right. So the 1 and -1 are the lane IDs. So these are, so you've got the S direction, you've got your T axis here, and this is the lane IDs. Then the next question is, when the super elevation of the road changes, will you create a new record or a section for it to be defined? So only one super elevation can be applied to a road elevation profile, or are there any methods to combine the two while allowing to be changing? I will have to check that in the specification. I think you can apply several super elevations to one road, and then there is an interpolation between those two. But I will check that in the specification and come back to you, Jason. Are successor and predecessor interchangeable? Depends on how the direction of your reference line is. So if you turn your reference line direction around, then your successor and predecessor would be interchangeable. In the end, they indicate a connection between two roads. Does the direction matter? Also, in a big network, you might not be able to reach a consistent direction. So no, the direction of the reference line actually doesn't matter in matters of driving direction. I guess that the next question is regarding the parameters of the third order polynomials. Should a user decide significant figures for each parameter? That is a good question, depending on what you want to achieve. So please choose the parameters for those third order polynomials so it fits your use case. Then we have the question, is there a length limitation of OpenCRG and OpenDRIVE? No, there isn't, at least not from the format side. Probably you will run out of memory at some point, because very long defined OpenCRG stretches can be quite memory intensive or storage intensive. So in the matters of performance, you will drop probably, but as from the format side, there is no limitation. How to compute the width if lane have multiple width entries? Yes. That is what I want to talk about in the next tutorial. Like what I can, I can send you the link to the specification. You've got the offset, and then there's the third order polynomial. Then what you add together then. Can you loop the CRG data for long roads? No, you can't. Unfortunately, not yet. How to get the stop line on road ID 2. So that was from the example I showed when I defined that road here. And that stop line would actually be an object that is then placed on that road ID 2. So you would define the object of the stopping line and then have that placed on that road. Okay, then there was a question on, can you explain again the sign conventions of roads in OpenDRIVE for driving directions? I think what you mean is, how does the direction of the reference line impact my driving direction? So in that case, my reference line goes from the left to the right. And that's just the way I define the s-axis. From the point of view of driving direction, and here I have the rule right-hand driving, I would start driving on the upper lane towards the left, and on the lower lane towards the right. But I could also turn around the reference line in road ID 1, and that wouldn't have an impact on the driving direction. It just would be a different definition of the reference line and the S coordinates in that case. So for road ID 1, I have S equals 0 at that point here, and S equals 100 here. And if I would turn that around, then S equals 0 would be here and S 100 here. I hope that answers the question. Okay, then we've got the next one. Artificial landmarks are squares containing a unique QR code usually attached to a wall or column near a road, but not on the road. I was thinking of encoding landmarks as objects, but object must belong to a road. How would you encode landmarks in OpenDRIVE? Any chance an object can be unlinked from a road to another element? Yes, you can place objects in the inertial coordinate system. That is possible. And what you could also do, you could add an object using corner local in a local coordinate system and then put that beside the road. That is also possible. So please refer to the new specification of 1.6 on the ASAM page. Then the question is here, is there a plus-minus sign convention for driving direction? No, so far we only have the rule of right-hand traffic or left-hand traffic. Then we have parking spaces in schema 1.4 are type object. Is this the best way to represent them, or is there another? There's a lane type. So you, for example, if you've got a parking bay, you could define that as a parking as well. But yes, that still is the case. If you want to define an individual parking space, there are still places objects. Sometimes it is hard to set super elevation in complex junctions. Yes, and that is something we want to tackle in the next standard development project, because when you have all of those overlapping roads in junctions and you want to apply super elevation or just anything else in case of elevation to a junction, that is really painful to do. So yes, I agree, and there is no solution in OpenDRIVE 1.6 yet. But that is something we want to tackle in OpenDRIVE 1.7. Why the elevation slope of road affect the calculation of road length? Yes, it will. So from a bird's eye view, your length will stay the same. And when you add elevation to the road, then that will increase the length of the road. Okay. Then we've got, how can you calculate super elevation? We've already got that. So the super elevation of a complex junction would need to piece together all the individual roads, also the overlapping roads, and align the super elevation of all of those individual overlapping roads. What is the difference between road file format XODR and XODRZ? So I guess that the XODRZ is the zipped version of the XODR. But that probably depends on where you get your files from. So the standard OpenDRIVE file format ending is XODR. Then we have the question, controllers refer to signals, road signs, barriers, bumps that should control the behavior of cars on a road lane. I see the link in the schema, but how do you encode the rule? Right of way, stop at barrier. So controllers are there for traffic lights. Signals have their own rule. So the rule is defined with the signal. Depending on where you are. and depends on what you want to encode. So if you want to have very complex rule encodings, that might be something you would need to do in the simulation. Is there any method? Is there any method that let OpenDRIVE file generated from OpenStreetMaps a smooth road structure? I guess there are probably methods to do so, but there's nothing defined in OpenDRIVE for that. So how to convert from OpenStreetMap to OpenDRIVE, that is not the responsibility of OpenDRIVE. So I know that I think there are a few projects out there that are tackling that issue, and the problem here is that the data quality in OpenStreetMaps differs quite significantly between different sections. So yeah, but if you've got a high quality section in OpenStreetMaps, there's all the information probably in there to create an OpenDRIVE file. Then we've got a question, is there a bounding box or dimensions for the junction, example, length or width? The answer is no, not yet. So you could probably calculate that from all the connecting roads, but that is something we will also tackle in the 1.7 project. Then we have the question, can we create corner cutting at junction? I'm not quite sure what you mean by that, but I guess you want to cut a corner like this, so you probably would have to define a road that goes a bit smoother than my perpendicular corner here. So that is not a realistic example. So then we have the answer, in future releases, will it be possible to use spirals to describe borders instead of cubic polygons? That is not planned, but if that is something you feel necessary, I can just invite you to join the next OpenDRIVE development project, and then we can discuss it with the whole project group. That is not yet set up, but we are planning to do that in the next project. Okay. Okay, then we have a question regarding OpenCRG. Is the grid size in OpenCRG fixed or variable? The answer is clear, it's variable, and you can choose any resolution you want or your system is capable of handling. So if you would like to do a grid resolution of a few micrometers, that would be possible, but you would end up with a lot of data. So yes, the answer is it's variable. Okay. Let's see if there are questions in the chat. And I think we are through all the questions. Then thanks everyone for joining today.